Okay, guys, so let's get started. We're talking about Chernoff bounds today. Does anyone have any questions about the first part of the lecture? All right, anyways, I'm going to go through parts of this, and then I think I'll talk about a new problem also. Okay, so these Chernoff bounds, so again, the point here is to analyze how much a random variable is going to deviate from its expected value. Okay, because oftentimes when you analyze these randomized algorithms, you can get the expected value of some random variable, for example, the running time or the error probability. Okay, you can usually bound the expected value pretty easily because you have this very powerful tool of linearity of expectations. But we want to say more than just the expected value. You also want to say something like, well, this variable is very unlikely to be quite different from the expected value, right? And the point of these Chernoff bounds, and also the other bounds like the Chebyshev bound and the Markov bounds, the point of all of these bounds is to say, what is the probability that this variable x that you have is very different from the expected value? Okay. Oh, guys, you cannot hear? Can other people hear me? Okay, Huangjie, I don't know. Can you try logging out or something and then coming back in? Yeah, I'm sorry about that. Yeah, I mean, I know, Tencent is the other option, but problem is I had some problems using Tencent, and then, I just couldn't keep the meeting, available all the time. So that's why I'm moving to Zoom. Anyways, if you have audio or video problems, I think just try logging out and then coming back, and usually that fixes the problem. Okay? All right, so anyways, so we talked about the Markov inequality, right? Any questions about the Markov inequality? Okay, yeah, so it's useful because it's very general, but it gives weak bounds, okay, the Markov inequality. Okay, so then we have a somewhat stronger inequality, the Chebyshev inequality. This one is a bit harder to use because for the Markov inequality, the only thing you need is to be able to compute the expectation. Okay, and usually that's easy. Okay, but for the Chebyshev inequality, you also need to compute the variance. Now, for for simple random variables, right, like this example I gave with flipping a coin, so there you can do the variance pretty easily, right? However, as you move to more complicated random variables, then even computing the variance can be sometimes kind of challenging. Okay, so yeah, so the Chebyshev inequality usually gives stronger bounds than Markov, but you have to go through this process of somehow computing the variance. Okay, now before we talk about the Chernoff bound, I want to introduce another problem to you guys. Okay, so this problem is called the coupon collector problem. Okay, so this is like a very classic problem in the analysis of randomized algorithms. Okay, so it's called the coupon collectors problem. Okay, yeah. So let me just give you sort of the setup for this problem. So so imagine that you go to some restaurant, okay, your favorite restaurant, and then every time you go, they give you like a little coupon, and the coupon has like a nice picture on it. Okay, so let's say sometimes it's got a picture of a cat, right? A nice kitty cat, and then sometimes it's got a little doggy on it, and maybe like a panda or something. Okay, so they got a bunch of these coupons, and let's say there are like 20 different types of coupons. Okay, or in general, let's say that there are n different coupons. Okay, and each time you go to the restaurant, they give you a random one of these 20 coupons. Okay, and then because these coupons are so nice looking, you want to collect all of these coupons. Okay, but again, the problem is that each time you go, they just give you a random coupon. So even, for example, if you already have the panda coupon, right? So let's say last week you got the panda coupon, and then this week you go again. Okay, you still might get another panda coupon. Okay, and so what you want to do is You want to figure out how many times do you have to go to this restaurant before you can collect all of the different types of coupons. Okay, does that make sense, what I'm saying? Okay, so you have n different coupons. Every time you can take a sample, you can call it. Okay, and then each sample is a random one of these coupons. And the question is, how many random samples do you have to take before you can get all of these coupons? Okay, so that's the coupon collector problem. And so the number of samples you take, right? So let's call this x. Okay, so this is going to be a random variable, right? So it's a random variable, and equal to the number of coupons you need to, number of samples you need to take before you get all the coupons. Okay, so now first of all, do you guys have any guess what x is going to be? Like asymptotically, do you have any guesses? Right, all n coupons. So let's say that we have n coupons in total. So what do you think? Any guesses what x is approximately equal to? So for example, is x going to be very large? Is it going to be like exponential? For example, x, all right, let me add a question mark here. Is this going to be something like 2 to the n? What do you think? How many people think it takes many, many samples before you can get all the coupons? Okay, so I should say the expected value, right? Sorry about that. The expected value. Okay, all right. So so yeah, we have something even larger than 2 to the n. So yeah, so one suggestion is that e of x is actually equal to n factorial. Okay, so that would be very, very large, right? So even to get those 20 coupons, that would take you like 20 factorial, which is like, I don't know, like millions and billions of times, okay? What about other people? Do you guys think it's very large or not so large? Any other guesses? What about, let's say something like, n squared, okay? So how many people think it's going to be at least n squared? Right, okay, so does that mean the rest of you think it's going to be less than n squared? Okay, well, yeah, maybe you guys don't want to guess because if you don't, all right. Okay, so we got a guess of n squared. But does anyone think it's going to be less than n squared? Or does everyone think it's going to be at least n squared? Okay, all right, so we have a guess of n log n, okay? Yeah, so n log n is less than n squared, and actually n log n is the correct guess, okay? So in fact, what we're going to show is that this is equal to, let's say, order of n log n, okay? But in fact, you can be even more precise than this. You can say that it's going to be equal to n times the natural log of n, okay? Plus, what do we have? Is this little o or big O? I think it's big O, okay? It's going to be like this with high probability, okay? Or let me write this out with high probability. Okay, yeah, so in fact, it actually doesn't take you that many times before you get all the coupons, okay? It only takes you n times the natural log of n number of tries before you can get all the coupons, okay? And then here you have to add some like big O of n term, okay? So it's definitely big O of n log n, okay? So this bound is actually, so I'm gonna show this bound today. This is actually pretty easy to show, okay? This other one, this is more precise, right? Because It's saying that not only is an order of n log n, it is sort of like precisely n times the natural log of n. Okay, so this bound is more complicated to do. So I'm not going to do this bound. Okay, but if you guys are interested in getting this very tight bound, then just go ahead and look for the coupon collectors problem online. Okay, and I'm sure you'll find a nice proof for this. Okay, so then the first thing we're going to do is just to show, oh, you know what we're going to show today is with high probability. Okay, so I'm actually going to show that it's proportional to n log n. Okay, so maybe it's like 2 times n log n or 10 times n log n or something. Okay, so we can show this big O bound pretty easily. But if you want to get the constant in front to be very tight, right, then it's more challenging. Okay, so now the first thing to do is, when you make the statement, you're actually making 2 statements, okay? You're first of all saying the expectation is going to be this value over here, order n log n, okay? And second of all, you have to say, well, what is the probability that I get such an expectation, that I get a value which is close to that expectation, right? So you actually have to prove 2 things. You have to prove the expectation, and then you have to prove the probability you're close to the expectation. Okay, so the first thing we're going to do is prove the expectation. Okay, so then what we're going to do is we're going to define another random variable x sub I. Okay. All right. So before I do this, let me just tell you basically how the proof is going to go. Okay. So we're going to so our goal is to collect all n coupons, right? And then we're going to break things up into these time periods called epochs. Okay, so an epoch is between is the how do I say this? It's the time period between get a new coupon. Okay, so what I mean by this is you know, the first time that you go to this restaurant, you're gonna get the first coupon, right? And so the first epoch is like, how many more times do you have to go to that restaurant before you get your second coupon, second new coupon? Okay, you don't want the same coupon again, right? You want a new coupon the second time. Okay, so the first epoch is like the time period between getting your first coupon and then getting your second coupon. Okay, second type of coupon. Does that make sense? Okay, and then the second epoch would be the time period between getting your second type of coupon and the third type of coupon. Okay, and the third time period is between when you get your third type of coupon and the fourth one. Okay, now let me ask you guys a question. So xi equals the length of the ith epoch. Okay, so let's define this random variable x sub I to be the number of you know, trials you need in the ith epoch. Okay, so for example, if it takes you you know, if you have to go to that restaurant 5 times between getting your third and your fourth coupon, right, then x of 3 would be equal to 5. Okay, now do you guys think these x of I values are going to get larger or smaller over time? What do you think? Let's say the expectation of these xi values. Okay, right, so it's going to get larger, okay? And yep, so all of you guys are correct. And the reason is that, you know, between when you, so for example, when you, the first epoch, which is between when you get your first and second coupons, okay? Well, after you get your first coupon, there are many, many other coupons left, right? There are n-1 other types of coupons left, right? So the next time you go, it's, since you're going to get a random coupon, right? Then you're very likely, your probability is going to be n-1 over n, that you're going to get one of these new coupons. Okay, so each time, so after getting your first coupon, it's very likely that you'll quickly get your second new type of coupon. Okay. On the other hand, if you've gotten, let's say, almost all of the coupons, okay, so let's say you've gotten like n-1 different coupons already. Okay, so there's just one more left, right? But the problem is that the probability of getting that one additional coupon is only 1 over n. Okay, so as you go back to this restaurant, you know, each time you only have a 1 over n probability of getting that last coupon. Okay, so it takes you a long time to get that final coupon. Okay, yeah. So you guys are right that so these xi's are gonna in expectation they're gonna get larger. Okay. And then so then what is the expected value of x sub I, right? What do you guys think? Yeah, okay. Yeah, so Minzhang wrote this expression, so I'm just going to write it over here on the main screen. So let me let me do it this way. Okay, so it's going to be so the claim is that it's going to be n divided by m minus I. Okay, and the reason is that you know, in the ith epoch, you have how many? You have m minus I remaining types of coupons that you can get. Okay, so for example, in the first epoch, right, you have m minus 1 other types of coupons that you can get. Okay, so the probability you get a new coupon in the ith epoch is going to be m minus I divided by n, right? Because there are m minus I other types of coupons that you don't have yet, right? And then you get a random one of those, so you have that probability, okay, of getting a new coupon, okay, and so the length of the value of the ith epoch is just you know, the expected number of times you need to you know, try to get new coupons before you actually get one, okay, so it's just going to be 1 divided by this probability over here. Okay, it's kind of like, you know, if you flip a coin and then let's say you've got a quarter probability of getting heads, okay, then in expectation, you need to flip this 4 times before you get a head. Okay, so therefore, in expectation, oh yeah, right. So, because the first time, the first epoch is gonna just take 1 time unit, right? Because the first time you go, you automatically get your first coupon. Yeah. Okay. So then, yeah, so then the expectation of the ith epoch is going to be like this, okay? And now what we have is that we're trying to figure out the expected number of epochs to get all the coupons, right? But then this is equal to this sum over here, okay? And this is because, you know, this x1 is the amount of time. Oh, let me see, how am I defining this? Maybe I should do like m minus 1 over here. Okay, yeah, so this x1 is the amount of time between getting your first and second coupon, right? And then after you get your second coupon, then you try to get your third coupon. But then the amount of time is going to be this x2 over here, right? That's the time between you get your second and your third coupon, okay? And then after you get your second coupon, then you want to get your third coupon, right? And that's going to take you x of 3 time. Okay? So in total, the amount of time it takes to get all your coupons is just the sum of all of these xi values. Okay? Does that make sense? Okay, and so then now we can finish everything. And so all we need to do is, if you want the expected value of x, right, then that's just going to be this expected value of x1 plus the expected value of x2, right, plus the expected value of x and minus 1, right? Okay, and this is, again, linearity of expectations. Okay, so you guys see that, you know, time and time again, this is a very, very useful property, this linearity. Okay, and then this is just going to be, then this is going to be m minus 1 divided by n, right? That's the expectation of E1, of x1, right? Plus, oh, I'm sorry, got this wrong. It should be n divided by m minus 1, right? Plus n divided by m minus 2, oops, right? Plus dot, dot, dot. And then plus, in the end, we're going to get something like n divided by 1. Okay, you guys see this? Right? This is coming from this expression over here. Okay, and now what is the sum going to be? You guys know? Okay, so this is going to be n times, well, there's this thing called the nth harmonic number, okay? So the harmonic number is just, well, let me just do it like this, okay? So I'm just going to write this sort of approximately equal to, okay? This is approximately equal to n times the natural log of n. Okay, there's some lower order factors here. I'm just going to ignore those. Okay? So this shows that in expectation, the number of time steps is n log n. Okay, any questions about this? Probability is n minus, okay, yeah. So then, so Tianyi is asking if the probability is n minus I divided by n, right? Why is the expectation n divided by n minus I? So this is just a basic property. So you have these geometric variables, and then if the probability is like, is p, right? For each trial is p, then expectation to get first success, okay, is 1 divided by p. Okay, just like, you know, if you flip a coin, right? If you're, let's say it's an unfair coin. So if your probability of getting heads is like 1/4, then you, in expectation, you need to flip this 4 times to get a head. Okay. Yeah. Okay, so then we see that the expectation here is going to be n log n. And then now we can actually show something a bit tighter than this. So we can show that it's going to be order n log n with high probability. Okay, so the way we're going to do this is, so let's let this event, let's call it, what do we call this? F, okay? So F sub I, and then let's say superscript R, okay? So yeah, so this is going to be the event that let's say coupon type I is not collected in the first R trials. Okay, so let me explain this. Yeah, so let's focus on a particular type of coupon. Let's say coupon I. Okay, and then we want to ask what is the event. So this denotes the event that even after you do, let's say 100 trials. Okay, let's say R equals 100. After 100 trials, you still have not collected coupon type R. Okay, so that's what this f of I denotes. Okay, and now it's actually easy to compute this the probability of of this thing having different values. Okay, so you can show that. So this is going to be actually, you know what? Maybe I should just write this as an equation over here. All right, so okay, so the probability, oops, let's change to black. So the probability that f sub I super R is going to be 1 minus 1 over n to the rth power, right? Because all we care about is that we don't get type I over here, okay? And in each trial, you don't get type I with probability 1 minus 1 over n. Right? I mean, you get type I with probability 1 over n because you get a random coupon. So with 1 minus 1 over n probability, you do not get type I. Okay? But if this happens R times, okay, then the probability becomes this thing, right, to the rth power. Okay? And then now you can actually, you can estimate this. So you can say that this is approximately equal to, what is this? This is going to be negative R to the nth, negative R divided by n. Okay, so we can approximate this, this expression over here using this exponential thing. Okay, and so therefore, now let's set R equal to something like beta n log n. Okay, in that case, then e to the negative R divided by n is going to be, well, this thing is going to cancel, the n is going to cancel out, so then you have e to the negative beta log n, right, which is going to be n to the negative beta. Okay? All right, so then this shows that, you know, for one particular coupon, so what this means is that for one particular coupon type, okay, if you run for some number beta here, okay, so here beta is going to be something larger than 0, okay? If you run for beta times n log n trials, the probability that you still do not get that coupon is only going to be n to the negative beta power, okay? And now what you can say is that the probability that this x here, okay, so remember x is that x is the number of trials you need to get all n coupons, okay? Now what is the probability this value here is going to be larger than r, okay? So this means that either, so this is going to be equal to, let me just write the expression first of all, I equals 1 to n of this FRI. Okay, because the probability that it takes you more than r trials to get all of the coupons means that there must be at least one of these coupons, right? Either type 1 or type 2, all the way up to type n, that you still have not received after r trials. Okay, so we're going to look at the union of all of these possibilities, right? That we don't receive type I after r trials. Okay, and the only way for x to be larger than r is if one of these possibilities happen. Okay, all right, and now we can use the union bound to bound this probability. Okay, so the union bound says that this is less than or equal to the sum from 1 to n of the probability of these individual FRIs. Okay, right? And then so this, since we know that for these individual FRIs, the probability is n to the negative beta, right? So then we can say that this is going to be less than or equal to n to the negative beta plus 1. Okay? So then, for example, if you set beta to be 2 here, okay? So if beta equals 2, right? Then this implies that the probability that x is larger than 2 times n log n is going to be less than, if you plug in 2 over here, you're going to get 1 divided by n. Okay? And then you see that as you make beta larger, then you're going to get very high probability that x is going to be less than or equal to r. Okay, so this shows that the expectation of x is going to be order n log n with high probability. Okay, any questions about this? Okay, so this bound is still weaker than this other stronger bound that we can show, right? Because here, the constant factor in front is just going to be 1 in this case, right? So yeah, it's actually, you can show with high probability it's exactly n log n. Okay, here we only show that it's going to be 2 times n log n with high probability.